Alright, time for another DraftPhysics.com video presentation. So, as I have repeatedly pointed out, I do have numerous videos on the subject of the kinetic energy formula and some specific ones made on specific points regarding different parts of, how gravity works, how linear rotation works, how different things work, and in terms of kind of levers and gears and hydraulics and all of that kind of stuff. And 5-minute videos, and my expectation is that people can handle playing those videos or the substance of them and countering the what is stated to be a reasonable explanation of the observed reality. Okay, and they won't do that. But they do have an expectation, my opponents that I watch and play their videos, that somehow I have to respond to their arguments, but they don't have to respond to mine. So that's the duplicity. Alright, and then when I do respond, again, they ignore everything stated. So, again, what's the point, okay, if they're going to be non-responsive to what you're stating is the flaw in what they're doing. Their experiment has a defect, and you point it out, and they ignore it. So I already did this. Alright, so this Michael Falwell guy did an experiment where he got what I would call a preposterous outcome. Okay, I mean, it just doesn't make any sense. He drops a 1/4 mass from 4 times the distance, and it weighs as much, okay, as the 4 mass dropped 1 unit of distance. Not really a plausible outcome. Okay, I don't think reality works that way. So I pointed out from these images alone, you're saying, well, these aren't really equal spring compressions. So regardless of what kind of, what your little stick says, what the spring is doing is clearly different. So from one experiment to the other, the spring compression isn't the same. I can't really mouse over that, unfortunately. Anyway, yeah, it is strange when the image is built in. I can't do much. But anyway, you can see the one on the far right, and then the other two are just two examples of the other event. Okay, and so you can see that the compression of the spring is different, even though it's reading the same compression. That is, the little detector on the spring is saying these two compressions are the same pressure. And so I'm sort of making the argument, obviously the spring isn't up to the task, therefore it hasn't moved the compression of the coils, hasn't moved all the way through the spring yet, and so it's compressed the top coils more than it's compressed the bottom coils. Now, I think that's a reasonable way of understanding that springs take time to spread their pressure, and that maybe you're not going to get an exact reading at any one point in time. Now, obviously, the frame rates were terrible in this video, blah, 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 so it's not very useful. So I've already made the point, okay? I don't have any confidence that this experiment was done right. He didn't do any quick releasing. We don't even see him releasing the objects. He's releasing the 4 mass from 11 centimeters. I mean, any little error there matters, blah 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 blah. So yeah, fine, okay, you proved. Ian Gosling did the video with Play-Doh, and he came up with results that are completely different than your results. Just a fact. Now, he won't show us that because he didn't film it, because it didn't come out his way, so he didn't film it. Alright, but he's not redoing it, so, but clearly there's a problem with the experiments. You want to pretend there's no problem, they're all coming out the same. Go ahead and pretend whatever you want. I'm not really going to deal with people who are going to just pretend, okay? Right on the surface, you're going to pretend all of these outcomes are producing some sort of truly consistent picture of reality, because they're not. Okay, it's just a lie to imply that it's coming out your way. So bullshit. So again, I'll go back to the theory I'm arguing, okay, which is, first, you're out of theoretical luck here. All right, Just there's no other way. Gravity doesn't work the way you think it does. Okay, 2 units of force isn't 4 units of energy. No matter how many times you say it is, it isn't. Okay, it doesn't make any sense. It's a nonsense to say it. It's not how gravity works. It's not how things are moved in gravity. It's not how things acquire velocity in gravity. So blah 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 blah. It doesn't take 16 times the fuel to go 4 times faster. Yeah. It doesn't make 16 times the mess when you go 4 times faster. It's just bullshit, frankly. Believe it at your own disgrace, frankly. Okay, so I will go over some of this. So I did a little experiment with this, just out of curiosity. I said, well, how high do you have to drop something to double its weight? It amazed me that physics didn't really tell you this answer. I mean, it should be an answer everybody already knows, And it turned out to be around 1 centimeter is what I came up with. Now, the funny thing is, when I went through the whole math of figuring out 1 centimeter and how fast 1 centimeter would be, it turned out to be 1 mile an hour. And then I found out that if you square 22 miles an hour, right? So if you put it in miles per hour, 9.8, you put it into miles per hour, which is 22, and you square 22, you get 484 centimeters, which would be 4.8 meters, which is very close to 4.9 meters. So that made me feel kind of confident that, yes, that centimeter number is damn close to the reality, because it, worked all the way through the math. So it's not like something told me the right answer ahead of time. I found a correlation that confirmed it was completely incidental to what I was doing, which was just mechanically trying to find the right answer. Now, I'll have to go into springs a little bit in this video. This scale works because it has a coiled spring. Okay, it's not a compressing spring. It's a one big coil. Okay, and the big coil gets pulled and stretched. So, one could logically say that the people who make scales kind of know what kind of spring to use to get better results. And so maybe there does make a difference what kind of spring you're using will change how accurately your scale reads a weight. Now, who knows? How well it also can handle impulse, that is quick compressions and quick releases. Will also be part of that equation, I suppose. Some better than others, blah, blah, blah. But again, we don't have any, physics hasn't touched the subject, so we can't say, because physics hasn't done any of these experiments. Physics won't explain it to us. Can't go to the textbook and get the answer. So that's part of the fraud here, is that why isn't all this been already done? I mean, why should we, at this late date, have to do all this crap? Yeah, that doesn't show up very well, but too bad, I guess I will say. It's not terribly important because I'll just redo most of it. So this up here, okay, this is 16, 4, 4, and 16, okay, using these different masses. And so the experiment Michael Falwell did would be, he dropped the lightweight from 16 centimeters, you could say. Okay, we're just doing the 4 to 1 thing. So this is going to be 4 centimeters to 16 centimeters. Okay, 1 unit of distance times 4 units of distance, and the 400. And obviously these numbers aren't anything close to, okay, the numbers he got. He got the same weight for both objects. You do have to do this subtraction, so it gets a little better because you're doing 1200 minus the 400. So it's really 800 to 400. So it would be, your expectation would be that the quarter mass would be half the compression. And he got it making almost the same compression, which is nonsensical, frankly. Just doesn't make any sense. It can't be made to make any sense. Then excuse me, Ian Gosling did this one here, where he takes the 400 gram from the short distance and then the half mass from the larger distance. And again, those numbers don't match. okay, in the sense that they're a little bit off. You know, it should be, is it the right two? 4, 6, half the mass, 4 times the mass. Yeah, so it comes out a little bit 1200 to 1000, you know, and so you can say, you know, it's not quite 50-50 until you subtract out the mass. So you have to minus 1200, so it's 800 and 800, so it would come out the same. Now, he got a pretty similar result, okay, using clay. So these two did equal each other. But frankly, the clay should still haven't done the subtraction part. So it should be that the heavy object should still produce a little bit more compression. Then that's what the theory says, okay? And the theory is just based on the fact that gravity is a consistent force and it causes a consistent effect, and you can calculate the consistent effect for any object. All objects fall at the same rate, so you can calculate how fast they're going, okay, and how many centimeters they're going to have to fall, and frankly what the expected energy would be when they impact the scale, like how much they're actually going to weigh if they start with a certain weight and 1 centimeter doubles that weight. So if it's true that 1 centimeter of height doubles something's weight, then that has an implication of consistency, and it all works out. So these numbers are just based on the fact that, yes, 1 centimeter doubles the weight, 4 centimeters, okay, 4 centimeters does this, it depends on what weight you're using, because you have to subtract the actual weight of the object, so that's the part that just throws it off. But obviously it's a doubling of the weight again, and then 16 centimeters would be a doubling of the weight again, always recognizing that you have to subtract the original weight of the object, because it's going to weigh the object besides weighing the impact. When the thing hits, it's going to hit with a certain force. Then there's also the force of its weight alone. Its weight in gravity will also impact the scale. So that's sort of what this part is about, but I'll just redraw that part and we can go over that, the origin of the effect. So I will do that. Alright, so we're back. I guess we'll talk about the springs first. Alright, so you have these different springs, and so the one in my scale is one of these type. So it's just this, and it's got a little lever on here, and it just basically pushes this down, and that is marked in increments of pressure, and that's how it measures, okay, how much something weighs. Then you could also compress a spring, or you could expand a spring. You could stretch a spring to weigh something, and all of these have their limitations. But again, we don't have any science behind any of it. We can't go to the How Do Springs Work page in the physics textbook and find out how fast springs can react. So part of my argument about Falwell's video is that, yeah, we have this different look to the two springs, and the sort of the argument is the spring compressed more at the top than it did the bottom. So in the one case it was more compressed here, and here it didn't compress the whole spring, where in the other case it compressed the whole spring. And so that's why this distance is different. It's because this is a smaller distance, because each one of the loops is compressed more. So in a sense, you really do have to have enough vision of the spring to see how much each one of these things, okay, each loop of the spring is actually compressing. And so maybe that's why that's why the scale uses the round spring, is because to avoid those kind of problems. Again, that would only be a problem in something that is going to hit with a velocity, and somehow the velocity can't get through the spring quick enough. We don't know how fast pressure moves through different kinds of springs. You can imagine like a car spring is really stiff, you know, on a car wheel, and that maybe only this first coil does all the action. You know, every time the car bounces, maybe it's really only bouncing here, you know, that first little coil is doing all the work. And so maybe it's not the best choice for measuring weight. All right. So just speculation. Again, their science doesn't say anything on the subject, so there's nothing to refute in terms of their argument. So they don't have one. So I'm just trying to explain why he possibly could get a wrong answer. Now, the fact that, again, that he didn't show us how he even dropped the objects, he didn't show us the measurements, didn't show us anything. So, frankly, you could say he could have made the mistake anywhere. We didn't even get to see how these, when he combines an object, he has one object and he's going to make 4 of them here, and he tapes them together. And, we don't even know if this alignment is perfect on us. This is on a rod. You could say that he could have this one a little bit off, and now it's rubbing on the interior pole because these aren't aligned perfectly. And so there's more friction when he drops the heavy one because they're not in alignment with each other and they're rubbing all the way down where they're not rubbing with the other one. So lots of perfectly reasonable explanations for a flawed or fake result. Alright, so back to the simple argument that you have a scale and you put something on the scale, a weight, and it weighs something. So it now weighs, it has a atomic weight, okay, it has a mass, and now we're going to let it give the scale a weight, and the weight is going to be completely created by the force of gravity. So it weighs nothing, right? If I have the scale this way, I can understand that the mass, okay, same mass, doesn't weigh anything, okay, without gravity. So gravity's creating the weight. All right, easy enough to understand. And the simple argument is you could argue that what's gravity doing? It's giving its motion. And how much motion is it giving it? And that's the key, is you want to find out. You say, well, what happens if I drop a weight from 1 centimeter and then let it fall on the scale? What does it weigh? Okay, now you could argue that if I do that, there's going to be the original weight. That is, I'm only dropping the one weight, okay, from 1 centimeter. But what's the implications of dropping that one weight from 1 centimeter? All right, so it's only 1 centimeter. What's the implications of doing that is I'll have this motion plus, okay, what it weighs. So I already know it compresses the spring a certain amount without me dropping it. So just putting it on the scale, it drops here, let's just say. And then when I drop it, I get it to double. So I get twice the distance on the scale when I drop it 1 centimeter. That means that this distance is the one I'm creating, and this distance is the one the mass is creating. So the dropping is doing one, the mass itself is doing the other. But I can understand that and say, okay, so in gravity, you're essentially falling 1 centimeter. It's the same thing. You sitting on the scale, okay, without being dropped, is the same weight, okay, as me adding an extra push, okay, of one mass going one velocity, which would be 1 mile an hour in this case. So if for 1 centimeter drop, it's 1 mile per hour. So that's how fast you drop in 1 centimeter. You get up to a speed of 1 mile an hour. That's what you're going to hit the scale with, is 1 mile an hour. All right. And so basically you're just saying that what happens when you drop the mass 1 centimeter is 1 unit. Let's say it weighs 100 grams. So 1 unit of 100 grams is just the weight of the object. You're adding 100 more grams, okay, by dropping it 1 centimeter. So now you have a total of 200. So when you go 4 times higher, all right, so you do the dropping from 4 times higher, and 4 times higher doubles your velocity. So that's all you've accomplished. You've just doubled the velocity. You haven't done anything else. That's all dropping it from 4 times the height does, is it doubles the velocity. You get 2x the velocity. Alright, so I was going 1 mile an hour from 1 centimeter. Now from 4 centimeters, okay, I'm going to be going 2 miles an hour. Alright. And 2 squared is 4. So that's where it's going to come out, and eventually where 22 miles an hour squared is 484 whatever, which is the same amount as 4.9 meters, that the actual distance you'll travel to get up to 9.8. To get 9.8 meters of acceleration, you have to travel 4.9 meters in the gravity. All right. Or 1 second. Yes, just very interesting. Anyway. So now you're going 2 miles an hour, okay, which is going to double one of these, right? So the 100 grams that you weigh, you still weigh. So that one's going to stay forever plus that. But this one you've just doubled now. So now you have 200, okay, grams worth of motion plus 100 grams. So you have a total of 300 grams is what you're going to weigh. All right. And then you go 4 times higher, so you go to 16 centimeters. Okay, and what you're going to do is double the velocity. The 2 miles an hour, you'll double to 4 miles per hour. Okay, 4 squared is 16. Now you're going to be going 4 miles per hour, and you're going to double this 200, so now it's 400. And it's going to be plus the same 100 grams. You still weigh 100. It still has a mass of 100 grams. The 100 gram mass is still going to affect the scale, so you have to add that, and that'll equal 500 grams of weight. So the weight will be 500. So the point is that this is consistent no matter what I change the 100 to 200. Doesn't matter where I do it. It doesn't matter which one I do it to. These mathematical obligations are obligations of gravity itself. Everything dropped from 1 centimeter weighs twice as much. Everything. Okay. Everything dropped from 4 centimeters is going to weigh twice as much as okay, gotta say that right. Twice as much as their mass plus their mass. Okay. Right. And it's going to be consistent, just going up. All you're doing is changing the velocity. Doubling the velocity just doubles the weight plus your actual mass. So you're doubling, the weight is the force of gravity. The mass, okay, is the force of gravity without any motion. That is, well, free falling. All right. So that's your challenge, okay? Just like in the other videos I explained, here's a gravitational body. You're flying by it. The speed you go will decide how much you're bent by the gravity. Those are the arguments you have to deal with, and you're just ignoring them. All right. Completely. Just pretending I'm supposed to think that 2 units of force, that is 2 units of velocity, is 4 units of energy, when there's no reason to think so. There's no logic to it. 2 units of force is not 4 units of energy. 1 unit plus 1 unit is 2 units. It's not 4 units. 1 plus 1 isn't 4. Alright, so maybe I'll deal with one comment. Just because it's such a stupid comment. But, I guess I should say something about it. Well, actually, there's a couple of stupid comments. So this is one that was on my website. So again, all these fake names, I don't really, happy birthday MI8 is, I don't know, you're saying what kind of retard has these silly screen names? This is so surreal. Okay, meters per second squared is just a way of writing units of acceleration. If that's all it was, then there wouldn't be an argument. I mean, clearly it's a way of converting 1 plus 1 equals 2 into 1 plus 1 equals 4. Clearly that's the reason why it's applied. That's the reason why it's contrived. So again, it's not non-consequential. It creates a different answer in a formula. To pretend it doesn't mean anything is just silly. Okay, it's not that complicated. It's incredibly complicated in the sense of it's so ludicrous and stupid. Why should I believe twice the velocity is 4 times the energy? Why? What in reality decides I should see that? Why didn't Newton see it? Newton clearly said 2 units of force, 2 units of velocity, 3 units of force, 3 units of velocity. He clearly said it. Okay, so he didn't see it. So you have to explain to me, why didn't Newton see it if it's not complicated? You're saying Newton couldn't see something that's not complicated? Why didn't Descartes see it? Why didn't Galileo see it? Okay. No, you don't square the seconds. Well, of course, you end up squaring exactly that. That's how you create the extra free energy, is you actually square how many seconds the object is in the gravity. You square that number and pretend it got 4 times the velocity instead of twice the velocity. Okay, because that's not how exponents work. Well, of course it is exactly how it works, and I don't know why you're making up this in preposterous fib to pretend that you're not going to square the seconds. Of course you're going to square them. So 2x, I don't even know what the x is for, squared. So x is the number you're going to square. Is that it? What's x? Okay, is not 4x squared. Doesn't matter, you're still squaring the x, whatever the x is. I don't know. What exactly is the x? The number of seconds it was in the gravity? That does not make sense. So I don't know what part doesn't make sense to you. Where did I argue that I just invented a 2 and a 4? I'm saying you're inventing the square. The square is the problem. There's 2 units of force. You're squaring it and saying there's 4 units of force. It's that obvious. So what the fuck, retard? So anyway, I guess I'll just block him because it's too silly a name. Frankly, who goes on the internet and does that kind of crap but a troll, frankly, a Farley sock account, for the purpose of wasting people's time. I'll go find the other nonsense comment. Alright, so this was pretty much the unwatchable Farley video explaining gravity, where he doesn't explain anything. He says it poorly, and he's basically just defending his experiment as somehow a real result. Blah, 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 blah. So just totally useless, frankly. Doesn't really deal with the gravity argument at all. Okay. So he says, let's see, I'll read his own comment. Yes, most of us earthbound dwellers are in gravity all the time. So who argued we're not in gravity? We're not free falling, are we? So I've clearly said you have to be free falling to collect the gravity. If you're not free falling, it means something's touching you and taking the energy away. So I've illustrated that in videos at least 100 times. So you can't see how you're just a liar and a cheater to imply that I said it some other way. See, this is how you evade the argument. You won't play the actual videos where I actually make the argument and point out these things, that gravity, okay, you can only collect velocity and gravity if nothing's touching you. If something's touching you, it's going to take the force from you. Perhaps if you reside in your head in the clouds on a permanent basis, gravity is a little different up there. So this isn't a physics argument of any kind. This isn't refuting any of the arguments I have made. It's clearly non-responsive to any of those arguments. It's clearly just evasion. He's clearly just a coward. Okay. As you say, it tapers off with distance by some sort of square law, I believe. So again, we know it's the inverse square law, and that's only because most gravitational objects have a center of mass, and it's a spherical center. And so the gravitational force, the paint, is being sprayed wider in 2 directions. And by spraying it wider in 2 directions, it becomes a squared function about how much of it can hit you. So it's exactly as I've stated, it's exactly how light bulbs work. So light bulbs work exactly by the same inverse square law, and it's just the inverse of gravity. So if you just, reverse the circumstance and say the photons are on the outside and they're heading for the single point source, it would duplicate gravity. So again, just lie about what I've said, lie about the arguments I've made, and play your little game. Okay. I forgot he likes to he likes the inverse square law. You forgot? He is okay with that squared function. Yeah, because it has a cause. It makes sense. How does squaring a velocity make sense in three-dimensional space? How does that make any sense at all? How does anything have a squared function of velocity? Okay. So shouldn't be let's see what else he said, issue for him hearing that pesky square word. Yeah, it's fine associated with things like squares, okay, or cubes. You could start to make some sense out of three-dimensional space. But nothing travels in three-dimensional space in something other than straight lines, frankly, okay, unless affected by a force. That's one of Newton's laws. It goes in a nice straight line until something interferes with it, okay? It doesn't go in a squared line. Fuckhead. Alright, here's the mindless comment. You can almost read that. See, I could probably move it over. Where the hell is it? Like this thing. Okay. Right. So I mean, it's just so they're such desperate cheaters that they can't fairly, they won't play my argument and then they'll cheat it so grossly. His statement: it matters how long you're in the gravity. Free falling. Yes, if you're standing on Earth, all of the energy gravity's creating is going into the Earth, and the Earth is feeling it. You're feeling it, frankly, sitting there. I've pointed that out. As you're sitting, you can feel yourself transferring the energy to the Earth. You can feel it happening. That's what I've said, you lying little sack of shit. Alright, doesn't make any sense whatsoever. So it doesn't make any sense to say how long you free fall in gravity will decide how fast you're going to go and how much energy and force you're going to collect. When, of course, that's exactly how gravity works. As long as you're close to the surface of the Earth, you are always in gravity. So again, no one's argued against that. The argument is you're not free falling, quite obviously, so you can't keep collecting velocity because it's getting sucked out of you by the Earth that you can feel pushing on you. Okay. It doesn't turn off when you hit the ground. So again, I've made exactly the opposite argument. I've said clearly that when you hit the ground, you have your impact force, plus you have your original mass that still has gravity affecting it. It still weighs something. You can't take away that weight. If you're moving away from the Earth, you are still in gravity. Okay, so again, now you're free falling in the sense that there's no force slowing you down or stopping you except gravity. So that's the only thing you're fighting, okay? And the only thing taking your energy is the gravity. Alright, but the field strength tapers off with distance. So again, nothing I haven't said exactly. Of course, but in none of these experiments does that have anything to do with it because, you have to go miles of distance, okay, before you change 9.8 to some other number. So none of that has anything to do with these experiments. Liar. I mean, these are just such pathetically bad arguments. I mean, it's so, just such evidence that they really don't know what the fuck they're talking about. G is called the gravitational constant. Well, isn't that so special? Why am I even... I won't bother reading Walker comments. He's way out there, nutter. Alright. So, bottom line is, we don't have any great spring theory besides Hooke's law, which is done without... Again, it really isn't. It isn't an impact weight law. Okay, it's just a weight law. A static mass law. and really doesn't tell us too much about the rest of this stuff, except that, yes, springs that have a lot of coils, you can expect them to behave more regularly than springs with very few coils. And so that might be part of the equation, is how do you measure exactly impacts with springs. And maybe there's just a limitation that certain springs can't balance the pressure across the entire spring fast enough, and therefore they won't compress. Okay, they won't give you a number, even though they have stored the force and they'll release the force. They can't give you a number. So that's another point to make up, is that the the state is they just for a lab video claims a subtly different reality. And those springs are also, they're bending. Okay, clearly the spring isn't staying straight. You had the weird effect of, in one case, the spring stored the energy and released almost all of it back, 90%. In the other case, it only released half as much back. So clearly something went wrong. So again, you want to keep denying that these experiments are flawed when they have, glaring flaws in them. Too stupid. Yeah, fuck you. It's just duplicity. So persuade Ian Gosling to man up and redo the clay experiment, the plasticine experiment that came out with the wrong answer from his perspective. And then you can explain all of the defects in that experiment and explain why that can't reveal the truth and that your experiments are somehow better. But have the balls to do that, because those answers were completely different than your answers. Completely different. Completely opposing. All right. So have the integrity to face the fact that the experiments aren't consistent, and that you have to explain why yours is better. The one you can't see, the one with the really bad frame rate, is the much superior experiment. Alright, anyway. Enough of the video. So we're still just waiting on the lever experiment. Any day now. Yeah, so hopefully it'll be soon. Okay, so yeah, not here yet. This guy is weird. Math and science. I get a ton of commercials. So he's like paying so much in commercials to get views. And you gotta wonder whether that works. I mean, how much he pays out, for how many views he actually does get. It'd be interesting to see those kind of numbers, whether it works at all. Okay, so enough of that. LK99. Oh, okay, so this is just more crap about the fake, superconductor. Anyway, till at room temperature superconductor. Blah, 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 blah. Alright, till the next time and such. I think that's it. Yeah.